So these are the notes for 3.3, which is all about properties of functions and their graphs. So the first thing we're going to talk about is behavior. One of the behaviors that we can talk about is increasing, decreasing, and constant behaviors. Increasing just means that as x increases, y increases. Graphically, what that means, I should draw a picture for you. Graphically, what that means is as x increases means as you go to the right, y increases, which means you go up. So increasing looks something like that. As you go to the right, the graph goes up. Okay. Decreasing means as x increases, y decreases. So when you think about that, that means as you go to the right, the y value should go down. So it's going to look something like that. As you go to the right, it goes down. And then lastly, constant behavior. As x increases, f of x remains the same. So what that means is, as you go to the right, the graph does not go up or down. So it's just always the same. Okay? Now, when you talk about these behaviors, you're going to be writing intervals for them. So intervals where it's increasing, intervals where it's decreasing, intervals where it's constant. There's a couple of things to bear in mind when you write these intervals. The first one is that you always use the x values when you write the intervals, never the y values. It's always x. The second thing to bear in mind is we always exclude the endpoints. We always use parentheses on them. The reason why is at the endpoints, the behavior is usually changing from one type to another, and so we really can't include that endpoint because it's not one or the other. It's something where it's changing. So we just always exclude the endpoints. All right, so let's look at an example of this. So example 1 here asks us to state the intervals on which each given function is increasing, decreasing, or constant. So I'm going to say increasing, and I'm going to use INC for the abbreviation of it. So I want to find intervals where it is increasing, where it is going up as I go to the right. This bit is going down as I go to the right. This bit's going up, so that would be an increasing bit, and this bit's going down. So the only increasing part is right here. And where does this part start? It starts right here, and the x value is 0. And then where does it end? It ends right here, and the x value there is 2. So we say it's increasing from 0 to 2. All right, decreasing, that's the areas where it's going down. So it's going down right here, and it's going down right here. So we have two different intervals. This first one starts at negative infinity, and then it keeps going down, 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 until we get to here, which is 0. And we'll put a union. And then our next interval is this little bit right here. It starts at this point, which has an x value of 2. And then it continues going to the right, and it's going to go to infinity. Please understand, I know this arrow points down, but it's also pointing to the right. And when we talk about this, we're talking about x values. You don't want to say 2 to negative infinity, because this arrow doesn't say it's going to negative infinity in the x. It says it's going to positive infinity in the x. It's going to negative infinity in the y, and you don't want to use y values when you write this interval. So do be careful with that. All right, the last one is constant. For constant, do we have any places where it's always the same? No. It's down, up, down, so there's no places where it is constant. All right, for our other one, we have increasing. Where is this increasing? Well, it's going up right here. It starts here at this point, which is 0, not included. And this one's doubly not included. It's also got a hole there, so we would definitely not include the 0. And then it keeps going up, 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 and it's going to continue going up to the right to infinity. Right. Decreasing. Any places where it's decreasing? No, there's nowhere where it's going down, so we'll say no. And then lastly, for constant, this one actually does have a constant interval. There's this little horizontal piece right here. So it starts here at the left, which is at negative infinity, and it continues to be constant all the way until we get to here, which has an x value of 0. constant from negative infinity to 0. Okay. That's pretty easy to do. All right, the next thing we're going to look at is relative extrema, which are relative maximums and relative minimums. A relative maximum happens when the graph changes from increasing to decreasing. A good example of this you can see in this picture. It's going from increasing to decreasing. So this point here where it changes is a relative maximum. Okay. A relative minimum, on the other hand, is a place where the graph goes from decreasing to increasing. So you look here, it's decreasing, and then it's increasing. So the spot where it changed from decreasing to increasing is a relative minimum. Now, it is possible for a graph to have multiple relative maximums and relative minimums. You don't necessarily just have to have one. You could have more than one. You can also have none. It could be a graph where you don't have any relative maximums or any relative minimums. So just be aware that it's not necessarily one final answer. It could be multiple, or it could be none. The other thing to be aware of is that some textbooks use the word local instead of relative, but it means the same thing. Local and relative are just synonyms. So if I say local maximum, it means the same thing as relative maximum. Or if I say local minimum, it means the same thing as relative minimum. Okay. Let's look at this next one. So example 2 here asks us to look at the graph of the function below, and it lists intervals where f is increasing and decreasing, then determine what value of x, if any, f has a local maximum, list the local maximum value, and then determine at what value of x, if any, f has a local minimum, and then list the local minimum values. We've got quite a few things to do. So the first part asks us to write intervals where it is increasing and decreasing. Well, it's increasing from here to here and from here to here. So this first interval starts at an x value of -1 and continues to this point, which has an x value of 1. And then the other interval is right here, which starts at an x value of 3 and continues on to infinity. For decreasing, we have an interval right here where it's going down, and we have an interval right here where it's going down. This first one goes from negative infinity on the left all the way until we get to this point, which is at an x value of -1. And then the second one goes here, which goes from an x value of 1 to an x value of 3. Okay. The next part asks us to figure out where we have a local maximum, at what x value. So, when we look at the graph, we want to see, are there any places where the graph changes from increasing to decreasing? And there is one spot, this spot right here. It goes increasing, and then it goes decreasing. So that spot right there is a local maximum. So it happens at x equals 1. And then it asks us to find the local maximum value. When they talk about value, they're talking about the y. So what is the y value at this point? The y value is 2. So the local max is located at x equals 1, and it has a value of 2. All right. The next thing asks us to find what values of x f has a local minimum. So we'll say local min at, and we want to see what x values that would be. Remember, minimum means decreasing to increasing. So there's actually one right here and one right here. This one is going decreasing and then increasing, so that's a local min. This one right here, it's going decreasing and then increasing, so that's another local min. So we have a local min at x equals -1 and at x equals 3. Okay, so one here and one here. And then the last thing asks us to list the local minimum values. So we say local minimum values are, and for this one, what's the y value there? Well, the y value is 1. And what's the y value here? The y value is 0. So this one has two different minimum values. It has a minimum value of 1 and a minimum value of 0. And again, that's okay, because again, we're talking about local or relative. We're not talking about anything else. Okay? Just be aware of that. Alright, the next thing we're going to talk about is absolute maximums and absolute minimums. So it is possible if you're looking at a closed interval, meaning only from a certain x to a certain x, that the graph has an absolute maximum and an absolute minimum. An absolute maximum means what is the absolute highest point in this interval. Okay. So what is the absolute highest y value? Where is it at? Absolute minimum, on the other hand, is what is the absolute lowest y value? What is the absolute lowest point on this graph within this interval? And that's one of the things to stress right here is it has to be on a closed interval. If it is on an open interval, then you can't have an absolute max or min because your arrows are going to go off to negative infinity and positive infinity, and so therefore you don't have a highest point or a lowest point. It just continues to increase or continues to decrease. Okay. Now, what if one side is open and one side is closed? Well, if one side is open and one side is closed, then you might have one of the absolutes, but not the other. Like you might have an absolute max, but no absolute min. Or you might have an absolute min, but no absolute max. It just kind of depends on how it's closed and how it's open. Okay? So let's look at an example of that. Alright, so example 3 asks us for the functions graph below, find the absolute maximum and absolute minimum if they exist, and also locate any local maxima or local minima. So we'll start by looking and seeing, do we have an absolute max? Well, this is a closed interval. This graph only goes from 0 to 5. It doesn't continue beyond 0 or beyond 5. So it does have an absolute max somewhere. What is the absolute highest point? Well, it's right here. So the absolute max is at 3, 6. Okay. Absolute minimum. Okay. Because, again, this is a closed interval, then we can actually have a lowest point. What is our lowest point? Well, our lowest point's down here at 0, 1. Okay, so that's our lowest point, and that's our highest point. All right. The next thing is local maximum and local minimum. Okay. Local max. Do we have any places where it goes increasing to decreasing? Yeah, we do, right here, which is at 3, 6. Notice the local max and the absolute max happen to be the same spot, and that's okay. All right. Local minimum. For local minimum, remember we look for decreasing to increasing. Are there any places where it goes decreasing to increasing? Yeah, right here. It goes decreasing to increasing. So it's this point right here at 4, 4. And notice the local minimum is not the absolute minimum. They're different. The absolute minimum is way down here. The local minimum is only right there. All right. For our other graph, we have this graph right here. Okay. It starts at this point and continues going this way. So this is not a closed interval. It's open on the right-hand side. And because this right-hand side points down, that tells us we don't have an absolute minimum. This is going to continue decreasing forever, so there's not going to be an absolute minimum. So I can already say there is no absolute minimum. Okay. I can look for an absolute max, though. Okay, absolute max, what is the absolute highest point on this graph? Well, it's this point right here at 1, 4. Alright, and then if we look for our local max, we have places where it goes increasing to decreasing. And that's this point right here, which is at 4, 3. And then for local min, places where it goes decreasing to increasing. That's this point right here, which is at 2, 2. Okay. So there is absolute extrema. It's not too hard to do. Absolute maximum, then you're just looking at for the absolute highest and the absolute lowest, which is pretty easy to do. All right, the next thing we're going to look at is symmetry. Okay. We've already talked about symmetry a little bit. We talked about how to find it algebraically. We want to talk about what it means for graphs. So if a graph has y-axis symmetry, which means f of x equals f of negative x, then we call that function an even function. Okay? So even functions have y-axis symmetry. If a function has origin symmetry, which means f of negative x equals negative f of x, then we call that an odd function. So odd functions, origin symmetry. An easy way to remember this second one here is that origin starts with O, odd starts with O. Since they both start with O, they go together. So origin symmetry, odd. For even, you just have to remember even is y-axis. Okay? All right, so here in example 4, they asked us to determine algebraically whether each of the following functions is even, odd, or neither. I'll come back to this, but I want to scroll back to our definitions here. So even means f of x equals f of negative x, and odd means f of negative x equals negative f of x. So when we do this, we're going to check that for this one first. We're going to figure out what f of negative x is, and compare it to f of x, and see are they the same. If they're the same, it's even. If they're not the same, then we'll move on to this one. We will already have found f of negative x, because we found it up here. So what we'll do is we'll find negative f of x, and we'll compare those two. If those two are the same, then it's odd. If they are not the same, then we can say neither, because we will have already eliminated even and odd, and so the only possibility left would be neither. All right, so let's actually try and do that here. So for example 4a, we have f of x equals x to the third minus 6x. So the first thing I'm going to do is I'm going to find f of negative x. So that means I have negative x getting cubed minus 6 times negative x. When I cube a negative number, negative x times negative x times negative x, I'm going to get a negative x cubed. And when I take negative 6 and I multiply it by negative x, I get positive 6x. Now take that and compare it to the original. Are these two the same? No, these two are not the same. So we can say f of x does not equal f of negative x. So that tells us it's not even. Okay. Since it's not even, now we'll check for odd, and so we'll find negative f of x. Now negative f of x really just means negative 1 times f of x. So I'm going to take a negative 1, and then next to it I'm going to write f of x, which is the original function. Now take that negative 1, distribute it into the parentheses. Negative 1 times x cubed is negative x cubed. Negative 1 times negative 6x gives us a positive 6x. Okay. Now that we've found that, we compare it to this one. We don't compare it to the original, you compare it to the one right above it. So are these two the same? Yeah, these two are the same. So we can say negative f of x equals f of negative x. And since they are the same, that tells us this function is odd. Okay. All right, let's look at letter B. We got g of x equals x to the fourth minus 2x squared. So we'll start by finding g of negative x. So that's negative x to the fourth minus 2 times negative x getting squared. So negative x to the fourth, that's negative x times negative x times negative x times negative x. That's going to be 4 negatives, so that means it's going to come out positive. So it'll be positive x to the 4th. Right, here, negative 2 times negative x squared. Negative x squared means negative x times negative x, so that'll be positive x squared. Times a negative 2, that'll give us negative 2x squared. Take that, compare it to the original. Are these two the same? Yeah, these two are exactly the same. So we can say, f of x does equal f of negative x. And since they are equal, that tells us this function is even. We don't have to do any more work because we proved that it was even already. Alright, our last one, we got h of x equals x squared plus 2x plus 1. So the first thing we'll do is we'll check for even by finding h of negative x. So this is negative x getting squared plus 2 times negative x plus 1. When you square negative x times negative x gives you positive x squared. 2 times a negative x gives you negative 2x. And then we have the plus 1 at the end. Take that, compare it to the original. Are these two the same? No, they're close, but this is a positive 2x, this one's a negative 2x, so they're not exactly the same. So f of x does not equal f of negative x. Or, sorry, this should be h of x and h of negative x. And a similar kind of thing up here. Sorry about that. This should be g of x, and this should be g of negative x. Alright, go back to this. Because these two are not equal, that tells us this is not even. So then we're going to go and find negative h of x. So that means we have a negative 1 times our h of x function, which was x squared plus 2x plus 1. Distribute the negative 1 into the parentheses, and you get negative x squared minus 2x minus 1. Now compare this to the one right above it. Compare it to h of negative x. Are these two the same? No, they're different. This is a positive x squared, this is a negative x squared. This is a positive 1, that's a negative 1. They are different. So negative h of x does not equal h of negative x. So since those are not equal, that tells us it's not odd. So if it's not even and it's not odd, then our only choice is to say it is neither. So that's how you do even, odd, or neither algebraically. The last topic that we're going to look at today is average rate of change. So back in Chapter 2, we studied how to calculate the slope of a line. We said the slope was y2 minus y1 over x2 minus x1, which is right here. But what if we don't have a line? What if we have some kind of curve like what we have here in blue? Okay. Well, we can still find the quote-unquote slope between 2 points by doing y2 minus y1 over x2 minus x1. Now this is not really the slope. It's actually called the function's average rate of change. And it represents the slope of a line that connects the 2 points together. So right here, if I have this point and I find the quote-unquote slope between them, I'm not actually finding the slope of this blue line. What I'm finding is the slope of this black line called the secant line here. And that slope represents this blue function's average rate of change. Okay? Now, sometimes when we talk about average rate of change, instead of saying y2 minus y1, we use function notation. So we say f of b minus f of a over b minus a. A and b here represent x values. F of b is the function's value at b, so it's a y value at b. And f of a is the function's value at a, so it is the y value at a. So this is finding the change in y's, which we usually write as delta y, or over the change in the x's, which we usually write as delta x. So let's look at some examples related to this. So example 5 asks us to find the average rate of change for the function f of x equals 3x squared for x's that go 1 to 3, 1 to 5, and 1 to 7. So let's start with 1 to 3. So to find this, I'm going to be doing f of 3 minus f of 1 over 3 minus 1. Now f of 3 means I need to find the y value at 3. And to do that, I just plug 3 in for x here. So 3 squared is 9. 9 times 3 is 27. Minus f of 1, that's the y value at 1. So to find the y value at 1, I just plug 1 in for x. 1 squared is 1. 1 times 3 is 3. On the bottom, 3 minus 1 is just 2. On top, 27 minus 3 is 24. And then 24 divided by 2 is 12. So that's the function's average rate of change, its average slope, going from 1 to 3. Next one asks us to do 1 to 5. So this is going to be f of 5 minus f of 1 over 5 minus 1. So again, f of 5 means the y value at 5. So we're going to plug 5 into the equation and see what we get. 5 squared is 25. 25 times 3 is 75. Minus f of 1, plug 1 into the equation. 1 squared is 1 times 3 is 3. On the bottom, 5 minus 1 is 4. On top, 75 minus 3 is 72 over 4. So does 4 go into that equally? Yeah, it does. 4 goes into 7 one time, leaving 3 behind. We would drop down to 2, so it would be 32. 4 goes into 32 8 times. So we get 18. Alright, so that's our average rate of change, our average slope, from 1 to 5. The last one asks us to do 1 to 7. So this is going to be f of 7 minus f of 1 over 7 minus 1. To find f of 7, we plug 7 in for x. 7 squared is 49, and 49 times 3 is 147. Minus, when we plug 1 in, 1 squared is 1 times 3 is 3. And on the bottom, 7 minus 1 is 6. On top here, 147 minus 3 gives us 144 over 6. And then if we take 144 and we divide it by 6, we get 24. And so that's the function's average rate of change, or average slope, between 1 and 7. Alright, the last example. Our last example says, suppose that g of x equals 3x squared minus 2x plus 3. Find the average rate of change of g from negative 2 to positive 1, and then write the equation of the secant line that contains negative 2 comma g of negative 2. What I'm going to do first is I'm actually going to figure out what g of negative 2 is. So g of negative 2 means I'm going to take negative 2 and plug it in here. So 3 times negative 2 squared minus 2 times negative 2 3. And then I'm going to go to my calculator. And that comes out as 19. So that point that they're asking us about is negative 2 comma 19. Alright, so that's one of the things we're going to need in just a second. Let's go back to the beginning. We have our function, and they're asking us to find the average rate of change. Okay, going from negative 2 to 1. So that means we're going to have g of 1 minus g of negative 2 over 1 minus negative 2. To find g of 1, we're going to plug 1 in for all of the x's in this equation. So we're going to have 3 times 1 squared minus 2 times 1 plus 3. And that gives us 4. Minus g of negative 2, well, we actually found that just a second ago. G of negative 2 was 19. Put that in right there. On the bottom here, 1 minus negative 2, we have minus a negative. And remember, when we have minus a negative, that really means we have plus. So 1 plus 2 gives us 3. On top, we have 4 minus 19, which gives us negative 15 over 3. Negative 15 divided by 3 gives us negative 5. So this is the average rate of change. But remember, it's also the slope of the secant line. That's part of our definition. Okay. So when we get to this second thing, it asks us to find the equation of the secant line that contains this point, negative 219. Well, we have the point, and then here we just found the slope. So we just have to use our point slope formula. If you don't remember it, it's y minus y1 equals your slope times x minus x1. So if we fill this in, we have y minus, what is the y of our point? The y of our point is 19, equals, what is our slope? Slope we just found was negative 5 times x minus the x of our point, which is negative 2. And again, here you have minus a negative, so that's really a plus. So our final answer would be y minus 19 equals negative 5 times x plus 2. And if we wanted to, we could solve that for y, but they didn't ask us to here, so I'm not going to do that. But we could if we needed to. Alright, so that is it for our 3.3 notes. Again, if you have any questions, please feel free to send me an email.